Hello viewers, today in this program we are going to discuss linear programming and formulation. It is a very important part of business mathematics. It has application in almost every field of the life. The linear programming problem is an optimization problem. It is maximization or minimization. In this problem, objective function and the constants, these are the restrictions, are all linear function of variables. The constant may be inequalities or equalities. Linear programming problem was first recognized in 1930 by economists for optimal allocation to the resources. During Second World War, George B Dantzig, a member of US Air Force, formulated more effective procedure of allocating resources and termed it to linear programming. Its application in various fields are as follows: application in industry, product mix problem, blending problem, in production scheduling problem, subcontracting problem, in the application of management, media selection, portfolio selection, profit planning using linear programming problem. In the transportation, in assignment problem, utilize best manpower using linear programming problem. In the other field application like diet problem, in the agriculture field, flight scheduling, now we discuss the standard form of LPP. Its equation form is optimize Z is equal to C1x1 plus C2x2 plus and up to Cnxn. Here C1, C2, Cn are constants, while x1, x2, xn are decision variables. Under the condition subject to constraints, here are a11 x1 plus a12 x2 plus and so on, a1n xn may be less than, may be greater than, equal to b1. In the second constant we have a21 x1 plus a22 x2 plus and so on, a2n xn greater than, less than, equal to b2. In similar way, the mth constraint am1 x1 plus am2 x2 and so on, amn xn less than, greater than, equal to bm. Here variables all are non-negative, so we write x1, x2, x3 greater than, equal to 0. The standard form of LPP may represent in matrix like optimize Z is equal to CTX subject to constants Ax less than, greater than, equal to B and x greater than, equal to 0. Here the matrices C, X, B and A are represented as follows. Now we discuss the formulation of linear programming problem using some examples. Example 1 here is a firm manufacturing two types of electric items A and B can make a profit of Rs 20 per unit of A and Rs 30 per unit of B. Each unit of A requires 3 motors and 2 transformers, and each unit of B requires 2 motors and 4 transformers. The total supply of these restricted to 210 motors and 300 transformers per month. Type B is an export model requiring a voltage stabilizer which has a supply restricted to 65 units per month. Formulate the linear programming problem for maximum profit. Its solution is as follows. Let us suppose the company produce X item of type A and Y item of type B, and let Z be the profit of the firm. Therefore, the total profit Z is equal to 20X plus 30Y. Now, each unit of A requires 3 motors and B requires 2 motors. Available number of motors is 210 only. Therefore, the constant becomes 3x plus 2y less than equal to 210. Similarly, each unit of A requires 2 transformers and B requires 4, and available number of transformers is only up to 300. Therefore, 2x plus 4y less than equal to 300. B also required voltage stabilizer and only 65 of them are available. Therefore, y is less than equal to 65. Number of items of type A and type B can never be negative. Therefore, we write x greater than equal to 0 and y greater than equal to 0. On the basis of above discussion, we write the linear programming problem as its object function is maximize z is equal to 20x plus 30y subject to constraints 3x plus 2y less than equal to 210, x plus 2y less than equal to 150, y less than equal to 65, and x and y greater than equal to 0. Now, we discuss example 2. It is like this: a firm manufactures 2 items. It purchases casting which are then machined, bored and polished. Casting for item A and B cost Rs 2 and 3 respectively and are sold at Rs 5 and 6 each respectively. Running cost of 3 machines are Rs 20, Rs 14 and Rs 17.5 per hour respectively. Capacities of these machines are as follows: machining capacity for part A 25 per hour and for part B 40 per hour. Boring capacity is 28 per hour for part A and 35 per hour for part B, and the polishing capacity 35 per hour for part A and 25 per hour for part B. Formulate the linear programming model to determine the product mix that maximize the profit. Now, we discuss the solution of this problem. Let x and y represent the number of units of A and B to be manufactured per hour. The objective is to maximize the profit, and profit per part for item A and B is calculated in following table. Here in this table, we calculate the machining cost, boring cost, polishing cost and casting cost, and then total cost, so that we can find the profit after subtracting the total cost from selling price. Here are in first column these machine cost, boring cost, polishing cost, casting cost, total cost, selling price and profit for part A and part B are represented. Therefore, the objective function is to maximize z is equal to 1.2x plus 1.4y. Constraints are on the capacities of the machines for 1 hour running of each machine. They are 1 upon 25x plus 1 upon 40y less than equal to 1. Second, 1 upon 28x plus 1 upon 35y less than equal to 1, and for the third machine 1 upon 35x plus 1 upon 25y less than equal to 1, and x and y are non-negative. Therefore, x is greater than equal to 0, y is greater than equal to 0. This problem is on the basis of capacities of the machine. Therefore, we use here the less than equal to sign in the constraints, and since the capacity is given, the total capacity is always 1. So, we write here on the right hand side all less than equal to inequality equal to 1. Now, we discuss the third example. The third example is a firm manufactures headache pills in two sizes A and B. Size A contains 2 grains of aspirin, 5 grains of bicarbonate and 1 grains of codeine. Size B contains 1 gram of aspirin, 8 grains of bicarbonate and 6 grains of codeine. It has been found by users that it requires at least 12 grains of aspirin, 74 grains of bicarbonate and 24 grains of codeine for providing immediate relief. Formulate the linear programming problem. The least number of pills a patient should have to get for immediate relief. Its solution is, let a patient have to get X pills of type A and Y pills of type B. Therefore, the total number of pills is X plus Y. For immediate relief, the patient requires at least 12 units of aspirin, 74 units of bicarbonate and 24 units of codeine. Therefore, 2x plus y must be greater than equal to 12. 5x plus 8y must be greater than equal to 74 and x plus 6y greater than equal to 24. The number of pills cannot be negative. Therefore, we write x and y greater than equal to 0. On the basis of above discussion, the linear programming problem is formulated as minimize z is equal to x plus y subject to conditions 2x plus y greater than equal to 12, 5x plus 8y greater than equal to 74, x plus 6y greater than equal to 24 and x and y greater than equal to 0. Now, we discuss one more example. This example is like this. Old hens can be bought at Rs.20 each and young one at Rs.50 each. Old hens lay 3 eggs per week and young ones lay 5 eggs per week. Each leg being worth Rs.3, a hen costs Rs.10 per week to be fed. There are only Rs.800 available to spend on purchasing the hens, and it is not possible to house more than 20 hens at a time. Formulate the linear programming problem to find how many of each kind of hens should be bought in order to have a maximum profit per week. Its solution is represented as the matrix form of the given data are like this: hens, price, egg per week and feeding expenses. For old hen, it is 20 rupees price, laying 3 eggs, feeding expenses 10 rupees. For young hens, price is 50 rupees, lay egg 5 per week and feeding expenses 10 rupees. Let X old and Y young hens be purchased. Therefore, the total cost becomes 2x plus 5y. But amount available is only Rs.800. Therefore, 2x plus 5y must be less than equal to 800. Again, available space for the hen is only 20 hens. Therefore, x plus y less than equal to 20. Now, since x and y can never be negative, therefore, x and y greater than equal to 0. Here the equation 1, 2, 3 are constraints. Now, total number of x is here 3x plus 5y. Total income per week is 3x plus 5y multiplied by 3 rupees. Total expenditure per week is rupees 10 multiplied by x plus y. Therefore, the total profit per week is 3 multiplied by 3x plus 5y minus 10 multiplied by x plus y. That is, the profit is minus 1x plus 5y. Therefore, the linear programming problem becomes to maximize z is equal to minus 1x plus 5y subject to constraints 2x plus 5y less than equal to 800 and x plus y less than equal to 20 and x and y greater than equal to 0. After discussing these 4 problems, here we have discussed the problems in which less than type of inequality, we have greater than equal of inequality. Whenever something available and we are to use, we use less than type of inequality, but whenever we require, like in the problem of pills, we use greater than equal to inequality. Hello viewers, today we have discussed the linear programming and formulation. It is a very important part of business mathematics we have discussed. Here in this lecture, we have discussed about the introduction part and generation of this linear programming problem. It was generated by US airmen. In this lecture, we have also discussed the standard form of the linear programming problem in 2 ways. Linear programming problem can be arranged in equation form and it can be arranged in matrix form. Then we have given some examples to discuss the linear programming problem in detail. Here in the first example, it is the product mix example and the constraints are less than equal to type. Here in the second example, it is also the product mix problem, but here the capacities of machines are given. Therefore, we restrict our constraints to less than equal to 1. In the third problem, it is diet problem. It is the problem of medical science in which we find the minimum number of pills using the greater than type of inequality. In the fourth problem, we have discussed hen laying eggs and getting maximum profit from young and old hens. It is very interesting problem. So, I think you have enjoyed this lecture. Thank you.